Good afternoon and welcome to the Distinguished Lecture Series. It's my great pleasure to welcome Dr. Saul Griffith. Some of you would have seen the poster in terms of what a distinguished career he has had. He has a PhD from MIT in programmable assemblies and self-assembling systems, and material science and mechanical engineering degrees before that. He has a number of patents. He has launched a number of companies. And most importantly, he is committed to figure out how we balance carbon and economy at multiple scales, starting from the personal scale. And I'm impressed that he actually is going to bike down to dinner this evening. So he walks the talk, okay? So without further ado, so.
Thank you very much. So I guess I'm a scientist by training, but an engineer or a tinkerer by disposition. And today's talk, just to get you prepared for it, if anyone's having seizures watching me do this, you should leave now, because it'll be a random tour of my desktop. And what I'm going to show you now is what a company I started about 4 years ago, a project that I think is amazing, called Makani Power. This is where we're trying to harness high altitude wind power. And this is sort of gives context for the rest of the talk in terms of why I even started to think about the contents of the rest of the talk. So high altitude wind power, for a whole bunch of reasons, is really interesting. There's more wind at high altitudes in terms of the higher wind speeds and in terms of higher frequency of high wind speeds. The problem with high altitude wind power is how do you get there? So what I'm showing you, and I think this is totally amazing, is a completely autonomous aircraft that's flying. It's a glider. The power of the wind is making it fly in those circles. We have little turbines on the wing that are generating power. You can actually see the trace of the power being generated. It now flies in these circles. The airspeed is about 200 miles per hour. This is why you don't want a human on board. It's constantly pulling 8 or 9 Gs. And it looks, so this is a 6-meter wingspan. It's a nominal 10, 15 kilowatt machine. There's the turbines generating power. And it looks like at large scale, you can create electricity at maybe 3 or 4 cents a kilowatt hour, potentially a little cheaper doing this. What are the barriers to getting this to large scale? The natural size scale economically that this wants to be is sort of a 1 to 5 megawatt machine. So this is a 15 kilowatt machine. It's about the width of this stage. 1 to 5 megawatt machine of this looks like a 707 on a piece of string this thick that flies at 200 miles an hour in circles about 4,000, 5,000 feet up. And at this stage, you laugh at me and you walk out of the room. But you have to, it actually economically makes total sense, whereas a 1.5 megawatt traditional wind turbine will weigh about 140 tons. A 1.5 megawatt version of this will weigh about 1.5, maybe 2 tons. And so that saving in mass, it's made out of the same stuff, corresponds to a saving in cost of capital and et cetera, et cetera, et cetera. So the challenge is now to go from this. I think this is wonderfully boring. This video, you know how it was really exciting in the beginning? Now for the next 25 years, that thing just has to fly in that same circle. Right? So the challenge for this as a technology, you would think it's aerodynamics or mechanical engineering or material science. It's none of those things. The challenge is control systems. Can you put a sufficiently robust pigeon brain in silicon on that thing to keep it flying in all wind conditions for 25 years? If you can totally make very cheap energy. So to make a technology like this happen, before I had this video, I was trying to describe to people why on earth you would want to do this, and that's what led to the talk that I'm going to give today. Why is humanity at a stage where they're going to consider incredible technologies like that? So that led to this talk, and initially this talk was just about global energy potential, like as a physicist would look at this blue marble that we fly through space on, how much wind energy is there, how much solar energy, how much bioenergy, And it was a terribly impersonal look at the climate problem. As a narrative to public audiences, that wasn't very good, so that's why I've added the personal side of this story. It's actually been unbelievably educational for me. So here I was running a wind energy company. I looked at the energy use of the world, and then I looked at the energy use of me. Excuse me for having a lot of slides here that are sort of general audience. I'm assuming at Lawrence Berkeley I probably don't need to explain to people 1 joule of energy or the difference between energy and power. I try to measure everything in power because it's the rate at which we use energy, and I tend to think that the rate at which you use energy directly correlates in some respects to quality of life, and it's also a very useful mechanism for thinking about, there's the gag about 40 watts, I'm lifting a crate of apples every second, orders of magnitude of power. But the reason to do watts for me is you can take all the things you do on wildly different time scales, like flying so many miles a year, electricity bill, which is so many kilowatt hours per month, and things you do daily, like drinking a can of Coca-Cola or energy drink, and you can actually equate them all in one unit that's sort of helpful. So, if you're thinking about what I'm about to show you is in obsessive compulsive anal retentive detail my life in watts. If you just want the instant translation, if I tell you you have a 12,000 watt lifestyle, that means there's sort of 120, 100 watt light bulbs burning permanently. That's you, right? Or the joke is, that's not the glow of genius behind me, that's just the amount of energy I use. All right, so this is me. And because it's LBL and I'm going to show you some stuff that's sort of remedial energy, I'm actually going to do a sort of meta-narrative on the talk I normally get, saying, when I did this analysis, here were the open questions to me, here were the frustrations, here's where I think some research should be done, here's where I'd love to get some answers from the audience. Let's make this participatory, criticize anything I say that's wrong, help me if you know the answer to questions that I pose. So you can measure with reasonable accuracy, because I know exactly where I flew in the world. This was in 2007. I actually scraped the JetBlue, the American Airlines, and the Virgin Airlines annual reports. They tell you how many passenger miles they flew. They tell you how many gallons of jet fuel. And you can sort of get a good amortized value. And so, this is how many watts equivalent of power from my flying that year. It does not include the embodied energy of the aircraft or of the runways or of keeping the airports running. But we know this with high accuracy, right? This is probably the right number, plus or minus 10%. And I'm going to present my life in terms of decreasing measurable accuracy. I sort of really believe Galileo's quote, measure everything that is measurable and make measurable what is not. So this was my driving. I drove in 4 different vehicles or 4 different vehicle categories. I did about 10,000 miles in 2007. Most of it was in a Honda Insight at the top, 55 mile per gallon is what my wife and I averaged. We did about 4,500 miles, or roughly driving to New York via Chicago and Atlanta. I did a lot of driving in rental cars and taxis, sort of equivalent from New York to Boston and then back down to Key West. I have a diesel truck for work that I drove roughly from Key West to Jacksonville in the course of the year. The joke here is the only safe way to travel across the Southwest is in a pickup truck. And the only sane way to drive from Tucson to San Francisco is in your vintage 1959 Volkswagen dune buggy. So anyway, that was 10,000 miles, 1,500 watts. The average vehicle that I drive in is 2 or 3 times more efficient miles per gallon than the average American's car. And the average American drives 15,000 miles a year. So I'm actually really low on this, even though it sounds like I do a lot. Again, that's pretty accurate because I know how many gallons went into all these things. So I measured it. So let's call this value maybe plus or minus 20%. This is every heat or electricity using device in my home, the time series for 2007. You'll notice that I don't own a television, so my list of electric gadgets is actually pretty small. The majority of energy use in my house is overwhelmingly heat. The portion of lighting, for example, is tiny. Lighting is sort of that little brown thing at the top. Sorry?
Where's your hot water other than your
Hot water, well, so the shower is just, I just did from how many minutes per day I was showering. The rest of the hot water goes under gas heat, right? So this is the PG&E bill. I broke it down to the amount that you can separate it out by the measurement tools or estimation tools you have. That's the equivalent for my office, you know, sharing it for 40 people. Those things are quite accurate because they're your PG&E bill. This is not terribly accurate. We still have the best paper, for example, on the amount of energy to get a glass of wine to was written by a guy with a pseudonym, Dr. Vino. But he does a reasonable carbon calculation. You can back out energy. So for 2 glasses of wine a night, it's 76 watts. These numbers for farming, transportation, and fertilizer, they're actually Department of Agriculture, if you take the total amount of primary fuels that we put into those 3 activities and divide it by 300 million, that's what you get. Sort of loose estimates for cheese and meat and fish. So maybe 772 watts, plus or minus 200% error bars on this. So I think it would be worthwhile someone doing a really good energy budget, not just food miles, but like the whole food energy system. Then, we exist in society. So this is the PG&E and the diesel and gasoline bill for the US government. So they actually publish it every year, which is kind of nice. So if you take your 300 millionth share, we're all, my share of the US military is a 100-watt light bulb. I'd like NASA to use a little more and the military a little less, but I'm a nerd. Then you can get those things. But this does not include the embodied energy of the infrastructure. So it doesn't tell you how much energy went into making the roads or the battleships or the government buildings, et cetera, et cetera. Then you're a consumer if you live in America. I'm a consumer. This is all of my stuff. I literally had a pair of scales. I weighed everything that went in and out of my life for a whole year. I catalogued every object I own. If you go into the fine print down here, it's socks and underwear and aluminum foil and toilet paper and sort of ridiculous things. And then you estimate so you can estimate the embodied energy by the mass of the object. To get to a watts value, I estimate the lifetime of the object. So amortize the embodied energy over the lifetime of the object, and you get this. Some super surprising things. My 3-day-a-week New York Times subscription uses more primary energy than all of the light bulbs in my life. So, for me, getting a Kindle and unsubscribing is way better than anything you can do with compact fluorescents and LEDs. So lots of cool stuff is in the details there. But then I would have to say this is plus or minus 50% accurate, depending on the item. And the main error here is actually the time period that you amortize the embodied energy over. So if you put it all together, this is me. This is Saul Griffith in 2007. I was using about 18,000 watts. Going counterclockwise from midnight. All of those blue ones, these are individual flights. So this is San Francisco to Sydney. This is the miles in each individual car, the heat for a shower and the cooking, all of the electricity in my life here. The orange section is all of my food, heat and electricity for my workplace, all of the objects that I own. Up in that little light green wedge there, that's the PG&E bill for the government we just discussed. This green area here is, there's 4.1 million miles of roads in North America. They're an average of about 7 meters wide. They're, you know roughly the mass and composition, and the DOT publishes how much is asphalt and how much is concrete of those roads, and nominally they're all replaced on a 40-year time period. You can convert all of that to a per person watt value for the road infrastructure. It's about 300 watts. And then this non-accounted up here, that's the rest of my tax dollars at work, right? So I pay a certain amount of money in tax. The best way to estimate that you can sort of come up with is there's a number of BTUs that the country uses in total, the total GDP. You can get $1 per unit of, you can get a BTU value per dollar spent. And so if my dollars are spent through those mechanisms, it's a big whack. That'll be an interesting thing to come back to. So 18,000 watts. Is that a lot or a little? So actually, let's start with this one. So 18, the average American is 11,000 watts. I was 18,000, so I'm a little more than the average Texan. Californians are down here. This is one of those Al Gore slides that lets you walk around dramatically. I didn't mean that. It was funny, I guess. So that sort of puts you in the perspective of America. The thing I don't like about these statistics is they don't really take into account imported and exported energy across state borders. So I think the Alaskans are penalized here because they're absorbing in their per capita the cost of pumping the Alaskan oil down here, and there's things like that that pervert these statistics. So that was America. This is the global picture. So there's America in 10th place. There's some really funny outliers like Qatar, where the government subsidizes oil costs to keep sort of social stability, and then they just run air conditioners all day on diesel. Then my joke here to offend all the Canadians in the audience is you're just Americans who live somewhere colder, and that's why you're in 9th, not 10th place. Australians aren't that much better, that's me. Here's the top 50. The global average is 2,200 watts. What I think's scary about that is, let's go to the countries using less than 2,000 watts per person. I think this is 2005 data, so China's probably moved up a little. But 1.3 billion people at 1,600 watts, another billion people at 800 watts. It's Bangladesh and Haiti fighting out down to the bottom end per person. The scary thing about that is they're going to want to use more. So 18,000 watts for my lifestyle. Here I was running, I was a bicycle commuter running a wind energy company, claiming I was doing everything right, and I'm the problem, right? So I'll skip some things. You guys know this. So, okay, so why do we even care about this problem right now? This is really it. I don't need to show you guys. You look at these graphs all day. We're concerned about CO2. There's the long, medium, and short-term time series. You can do cumulative CO2 assessments since the Industrial Revolution. So this is the who's to blame slide. I won't say much. Then this is the cartoon carbon balance for the world. And I'm building up to an argument of here is like, how do you figure out what to do, given now this is the problem, right? Well, one way of looking at carbon is this way. We put about 8 gigatons a year in the atmosphere. 2 gigatons get absorbed in the oceans. About 50% of the difference is absorbed into the atmosphere. We're still trying to figure out why. We don't know where the rest of that goes. The scary thing is the amount of carbon in either of these places, in all the vegetation or all the fossil fuels. If you put all that in the atmosphere, where there's no way you stay at some sane number, so you've got to be concerned. The good news is there's a lot of the soils and the oceans are large potential sinks. Temperature records look bad. Anyway, so to get to the scientist by training but engineer by disposition, I'm sort of like, well, how do you engineer a real solution that actually adds up, right? And I think step one is you have to commit to the temperature you want, because then you can work backwards. And this is the great debate that no one politically wants to have. How would you go about doing that? Well, there are sort of 3 tools. We have the climate models. You guys understand them. They're multi-physics chemistry models. I think they're actually, when I first did this work, I was so horrified by the answer, I was convinced for a while that in all the climate models in the world, they were all running on the same postdocs, Fortran from 1980, and maybe they were all, it was all the same code and they were all wrong. But it took me downloading 3 or 4 different, because enough of them were open to figure out that no, they're actually doing great jobs, and I think it's good work. From those, obviously, we have scenarios. These are the guesses at humanity's reactions. And then we have the impact studies that make all the headlines. So I would like to at least logically think about the problem this way. And I'm sorry that this slide isn't coming out well. So on here we have year. So this is 2000, 2100. This is the temperature axis. So 0 degrees is here. Basically, as far as we can tell today with the accuracy of our models, this bar sort of says if you hit 450, here's the spread of probabilities of temperature. 2 degrees is there, 1.5. So you got, something like a 25 or a third or a 33% chance of staying below 2. And then those bars, error bars, get bigger, and the temperature goes up as you go up. So starting from that, obviously we know the scenarios. The thing that troubles me is even in our best case scenario, we're still 2 degrees, end of century. I'll come back to that. This is how people think about the impact studies. So you'd like to be able to go from the impact studies, choose the level of horror that you want from this list, pick a value, and then say, okay, let's work back from that. So let's just say that it's roughly right that we'll do 2 degrees, right? Which might be what they shoot for. So let's say you chose this sort of situation. We're prepared to accept the risks of going a little above 2 by hitting 450. Now you have a number you can work back from. Grossly, if you use the percentage model, which is in the public dialogue of carbon reductions, percentage carbon reductions by a certain date, this is sort of the valid cartoon of climate change, right? You basically have to balance this equation. So the carbon out, carbon in. I would prefer that we use, probably a lot of you know the name Jonathan Coomey. I think in the early 90s there was sort of this debate. We talk about carbon reductions in terms of percentages. He lobbied with Krauss and a few others to say, no, look, because of the long time lag in the atmosphere, let's just talk about it as about the number of tons you have to burn before you stop completely. I kind of like this because it gives you, for every terawatt year, you actually have a value of ppm you add. Scary thing about this is you've only got 60 ppm to go. It's 400 terawatt years left of fossil fuels, which doesn't add up to a lot by those methods. But, and that's the nice thing is this method of looking at things is coming back into the literature with this study in Nature. You can start to do an equation for humanity from this. I won't. In front of this audience, it looks naive, so I'll jump past it. All right, this is how we produce energy today. This is really exergy, not energy. I can say that here because you guys know what I mean. The IEA publishes a slightly different number, so that's why you hear 16 terawatts as the human demand. That's because they don't really account for the plant matter the way that the nerds at Stanford do. So this is where we use it today, right? Here's really our only 4 options, right? So this was sort of the, this is, now I'm sort of gone from my individual thing back out in the bigger picture. So, you guys know this, we have solar, there's a ton of it. There's actually surprisingly little gravity. So if you actually harnessed every single joule of energy out of the motion of the moon around the planet, effectively flattening the tides, you only get like 1/5 of humanity's power supply. Yet we still invest in tidal power, right? In some respects, I'm building an argument here that you should probably invest in renewable energy in proportion to the capacity of the resource, which definitely has not been the case to date. Geothermal heat, this one's hard to really convert to a terawatt number. So this is basically the flux of heat flow from these reasons. There's arguments for whether it's 30 or 40 terawatts. You could, in fact, extract geothermal heat faster, but you would be finitely cooling the core, right? Nuclear power, it's not renewable. Actually, doesn't look like we have quite as much of it as we want unless we go to breeder reactors. You would hope we would invest in that. Anyway, so this is the big picture. If you ignore nuclear and you're just saying you've got to do it with renewables, this is sort of a cartoon of about 1,000 research papers on resource estimates. Tidal, it's actually not that much. The thing that really surprised me, I'm a surfer, and that's why I like driving up California in a dune buggy. If you extracted the power of every wave on every coastline on the planet, it looks like only 3 terawatts in total, and you ruin the surf, which is not good. This one's fun. If you capture every raindrop at the altitude that it falls on land on every continent in the world, it's only of order the same amount of power as humanity uses. By the time it makes it into rivers, this is 7 terawatts. That's flow in every river in the world. We're already harnessing about a half a terawatt of that. Oh, thank you.
Tidal power.
I actually built a hand power generator that does 60 watts, but I tried to give a talk with it once and I lasted 90 seconds. Powering your own talk it makes the talk exciting. The thing that worries me here is, again, in terms of the debate about how to allocate resources, if you burn every living thing that grows on the planet every year, you get about 90 terawatts, right? On land, it's about 65 terawatts. And in some respects, that means, are we really going to give up 10, 20% of land area for biomass and biofuels? I think it puts an upper bound on that. Anyway, so going back to the engineering argument, we just saw what our options were. So let's assume that we can, through great efficiency programs in the US and Europe, compensate for the growth in energy use in India and China and hold magically the world at 16 terawatts, crossing our fingers. Assume that magically we can also use 2 to 3 terawatts of fossil fuel into the future because the oceans will absorb some of that. We've got about 1.5 terawatts of existing non-carbon today. You want to do about 11.5 terawatts of new clean energy, and you've got to do it with about those 400 terawatt years you've got to transition by then. So let's take a reasonably agnostic mix of 2 terawatts of photovoltaics, 2 of solar thermal, 2 of wind, 2 of geothermal, 3 of nuclear, and half a terawatt of biofuels. What does the world, I sort of wanted to think through, what does the world look like? What's the engineering resource, and then what does the landscape look like? So it's 100 square meters of solar cells every second for the next 25 years, deployed at about 15% efficiency in places with more than 200 watts insolation, so good sites, right? 50 square meters of solar thermal mirrors every second, so that's every second we're filling this room with mirrors deployed, 30% efficiency, which is maybe on the high side. These are reasonably optimistic answers. So 12 3-megawatt wind turbines every hour, or 100-meter diameter wind turbine, visualize that, every 5 minutes has to be built somewhere in the world. It's a 3-gigawatt nuclear plant every week for 25 years, right? I think the US has, it's upped a little recently with the tax break, but it's like 10 or 12 are planned to be approved in the next decade. It's just ever so slightly behind the schedule. It's roughly, again, this is napkin math, but it's 300 megawatt steam turbines every day for 25 years for geothermal. And just to visualize those 3 machines, they're buildings the size of this one filled with fancy stainless steel and a couple of mile-long holes drilled on either side, right? So it's a reasonable amount of engineering. Biofuels, so assuming that we use genetically engineered algae and we're getting 3% photo-efficient conversion, right? That would be a profound, like 3 generations ahead biofuel technology. It's still an Olympic swimming pool per second, every second for 25 years that you have to install, or something like Wyoming and Nevada as a swimming pool of genetically engineered algae, which worries me. Okay, so they were the depressing slides. Here's the optimistic slides. The US drinks 110 billion aluminum cans a year. Right, so here's the killer business model if you're Coca-Cola. You're no longer a drinks company, you are the world's largest solar thermal company. If you slice those cans in half and flatten them out, the aluminum can be polished to about 94% reflective. You could do about 200 gigawatts of solar thermal a year. Plus, you don't have to ship water everywhere. So you return to your 1950 business model, which is you deliver the sugar and the syrup and they use local water rather than trucking water all over the country. So Coca-Cola alone can solve solar thermal. Nokia makes 9 phones every second. I think Apple at the moment is about 12 phones a second. So Nokia, Intel, Apple, you need companies that big cranking all the time to do that sort of 100 square meters of photovoltaics. This is just a testimony to how quickly your slides go out of date. In 2007, GM made 1 car every 2 minutes. I have no idea now. It might be 1 car a week. So, if you think about it, so maybe GM and Ford combined, it's about that level of infrastructure to produce those 150-ton wind turbines, 1 every 5 minutes. So it is possible. A lot of people say, this is just the I think we don't do service to what we have to do when we call it a Manhattan Project or an Apollo mission, right? The Manhattan Project was a science project. The Manhattan Project is NIF, right? And I really hope they succeed. And the Apollo project might be space-based solar, right? But they don't solve the whole problem. It's much more like, you know, retooling for World War II, except Japan, Germany, England, America are all playing on the same team, playing nice kind of thing. Here's a total good news slide. So I told you it was 11.5 terawatts in 25 years, and you think that's impossible. The reality is we brought 10 terawatts of generating capacity online in the last 40 years. So there's some sort of precedent for this level of industrial activity. It's certainly not impossible. The amount of tonnage of steel and et cetera that we delivered for the gas and oil and coal industry isn't that much different. So it is possible to, I think we should sort of propagate this meme. It's not much different than what we have already done. Okay, but then let's think about some consequences. So let's assume that we do all that engineering. Let's think about the next step ahead. So here's power density maps for all of the renewables in terms of watts per square meter. But this is a tricky slide because they're all on different scales. If you normalize the scale, they look like this. So that's biofuels in the top left-hand corner, that's hydro, top right-hand corner. Solar is, you know, here, and wind looks like this. So I sort of went through this exercise, and I'm just going to show you some cartoon math so you'll believe me. So we know what the solar constant is, we know there's atmospheric losses, all these other losses. I think most of you will believe me that if you're in Greenland, you're getting about 90 watts per square meter, and if you're in Nevada, about 300 watts per square meter. Averaged year-round, day, night, everything. Technology efficiency, if you pick a number like 10 to 40%, and then a land area coverage, so for a really good solar thermal, you cover about 25% of the land with mirrors. For industrial scale photovoltaics installation, it's about 50% land area coverage. In reality, net, you're going to be like 10 to 20 watts per square meter for solar. Wind isn't as good as I was hoping when I was doing this. I was hoping this number was, say, high altitude wind power is just absolutely the answer. Not really. So let's take, with wind power, you've got to be fair and use land area representative, not cross-section of the sky. So for this, 3 megawatt wind turbine that's 100 meters in diameter, you typically space them sort of 10 by 10 on a grid. So it's, 33% capacity factor. It's about a megawatt. It's a megawatt per square kilometer, so it's 1 watt per square meter. In a really good unidirectional wind site, you can shrink some of those dimensions, so maybe 2 watts per square meter. High altitude wind power might get to 4 or 5 or 6 watts per square meter. Hydroelectricity, it's hard to say what the representative area is because it's sort of concentrated by terrain. But if you said for the Hoover Dam, the representative area was Lake Mead, the catchment area, it's about 3 watts per square meter. And really that's just a setup for the joke that genetically engineered algae in Lake Mead would be about 2-3 watts per square meter. So this is the physicist map of the world. So this square is all of the land area in the world. These are the countries ranked by land area from 1 to 233 countries or something. And then Renewistan is a new country of 10 terawatts of renewable energy. 2 terawatts of wind in this case, 5 of solar, 1 of hydro, and 2 of biofuels. Using those numbers that we just used for representative land area. The thing that worries me is Renewistan is now the 7th largest country in the world, and it's the lion's share of Australia, right, in size. So I think the reason to put this up is not to get all the press that it's not possible, but it's to say that you should probably be thinking now a little more about which one of these are higher density and which ones are lower, and you might have a more tepid investment strategy in biofuels as opposed to thin film photovoltaics or something. This is more like in a perfect world where logic-based reason drove government policy, you'd invest with some sort of math like this. Anyway.
I have a comment on that.
Yeah.
So you could have some redundancy, right, where you have wind and solar.
Absolutely. And once you look at this, it then says to you, hey, maybe we should invest in combined wind biofarms, or et cetera, et cetera. I agree. So there's a few wins, but I think that you go through these cartoons to focus your mind on the next 4 ideas you're about to have, which will be better, hopefully, than what we do today. Anyway, so some of these you don't need. This is if you use that sort of Kuhn-Krauss model of total amount of carbon burned till you have to stop at 450, or it's convenient because now you can say 1 joule of fossil fuel energy used today produces, it sounds like a tiny number, 4.9 times 10 to the minus 21 ppm, right? So, okay, let's do an experiment. There's 800 million cars in the world today. Let's say we go to 1 billion with some increase in India and China, and they're all going to be 1,000 kilogram or 2,000 pound electric vehicles. We're going to use 100 megajoules per kilogram a car as the embodied energy. It's going to add half a ppm to build those, right? 250 million green homes. We're sort of talking global average single family domiciles. You can do the similar math, you get about 9 ppm. What about for installing that solar on the wind and those things? And so the scary thing about that is like you use up maybe 19 of your ppm just building the infrastructure. And this is an argument that is more to say there's still a lot of people who believe we can do this iteratively, right? Oh, we'll just try this technology, this one, this one, this one. I think you want to sort of say, no, we've got to make bigger commitments sooner on things that logically make sense. Because you don't get to change the infrastructure 3 times and still hit your target. I'd like someone here to do this rigorously in an academic paper that's published. I don't think it's terribly difficult. It's really accounting, not physics. But it's sort of not on the radar as much as it maybe should be. All right, so back to me, putting myself back in the picture. So I looked at all this and I got depressed. I went through the 7 cycles of depression and recklessness and abandonment and what are they all? I can't remember. But recklessness bit was really fun. The depressive bit was not so fun. My wife didn't like me for about 3 months because I was turning everything off and being a depressed bum. Okay, so I thought, okay, I'll take it into my own hands. I'm going to make myself I post-fact describe it. My personal project right now is to invent my way out of my own environmental hypocrisy, right? So actually, I want that. I have a 1-year-old. I want a good climate outcome for him. I want a good climate outcome for me. It plays out, he was born last year. This is all going to play out in his lifetime. So as a thought experiment, I'm going to try and live at the global average power consumption, 2,400 watts per person. And you all remember what my life used to look like. So there it is, to remind you. This is what my new life is sort of going to look like to get to 2,300 watts. So the first thing I did is stop paying taxes. That's the one-liner relating back. And that's, apart from being a great gag, that's actually an unbelievably significant and important result. And I think it's something I don't benefit greatly from academic publishing. But I wish someone who does benefit from academic publishing would do this, is elucidate this issue, right? When Obama stands up and says, I want to invest in infrastructure rather than a stimulus package, you're like, holy shit, if you invest in the wrong infrastructure, you make all this worse, right? And the way the government spends your tax dollars, I definitely want it to change a lot, knowing what I do here about it being 3,000 or 4,000 watts of my budget. The troubling outcome is it tells you that you should just not earn any money, right? That's the answer. But we'll ignore that because it's just troubling. All right, so this is my new life. I fly once a year to Boston and then do some train travel up and down the East Coast to do all of my East Coast business. Once every 3 years, I fly to Sydney to see my parents and my son's grandparents. Once every 5 years, I go to Europe, try and do all my business in Europe in one hit. Once every 10 years, I go surfing in Hawaii, right? 983 watts. Strangely, that's still about the same. Proportionally, it's still the same, my air travel budget. Driving now looks pretty ordinary. So this is not the US, this is the Bay Area. You'll recognize this. I get twice a month to drive in a 55 mile per gallon car from San Francisco to Alameda. Once a month in the work van from Alameda to Palo Alto. 6 times a year, I get to go and see my in-laws in Sebastopol in a Honda hybrid, and twice a year I get to go surfing. For those of you who know me, this is a complete lie. I will not visit my in-laws at all, and I'll go surfing 8 times. But occasionally my father-in-law is in the audience, so I have to hand it to him. Now this is aspirational, meaning I haven't got there yet. I now call myself sort of a 6/7 vegetarian, meaning I don't become a nice person if I never eat meat, right? I've tried to become a vegetarian, but I'm down to maybe 2 days a week now, and it's good. I think it's probably because, I'm 220 pounds, I'm a really active guy, and I find it hard to get the calorie concentration I want out of all vegetables. But now when I eat meat, I know its first name, I know where it was raised, and it's really high quality, but it's sort of down to, I'm aspiring to once a week, but I'm maybe at twice a week. I'm completely lying to tell you I've gone down to 1 glass of wine a night, but I'll have it there. But, and then I made some assumption here again that if you go local and organic, and I did this about 2 years ago, that you make some big win there, but it's completely unobvious and untrue, So I still think we need better research and understanding of sort of the whole food system to know what the right choice is here. And I think the people who say local organic is the solution, the data that's starting to come out suggests that industrial agribusiness may not be as bad as you think in energy terms. It might, all sorts of other problems, but I would like some more science applied to that. And in terms of consuming stuff, right, my old stuff was a huge amount. And I now want to, I'm just going to, because it's a complex bucket of things, because it's everything else you do in your life apart from move or eat or get heated. I just sort of make the assumption that maybe if I own 1/10 as much stuff, or I own the same amount of stuff and I make it last 10 times as long, like they're kind of your 2 options. And I think this is really an interesting point about stuff. And I know I had a few meetings here today with people who think about this a lot more deeply than I do, but so for most objects they use some energy to produce and some energy in their life. As you make them more and more efficient in terms of the energy used during the life, the proportion of their energy in their making goes way up, and the only option you then have is to make really high quality things, right? So this is like, I said heirloom design at a conference once, and it caught on as a concept. Because I was like arguing we should make cell phones that last 25 years and everyone should live in a house like they do in Portugal where the infrastructure is 600 years old. But it starts to make you think that we do need to think a lot more about the time span of things. I think a lot about this in terms of green buildings. The more green buildings I see go up that look like they're going to last 25 years because they're made of paper and twigs, that really worries me, right? In some respects, the green buildings are those buildings that you see in places where they built infrastructure before fossil fuels, and they're 4-foot thick stone walls. They last 800 years. They're passively solar cooled, right? That's LEED platinum, 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 platinum. Something. LEED unobtainium. Yeah, that's what we should have. All right, so maybe some other little random thoughts that I'll throw in here, and then you're a really smart group of people, so hopefully we'll do a lot in question time. But on products, I was particularly interested in, I got obsessed for a while, as you can now see that I do, about this thing. We were giving this away in the refrigerator that we had at my wind energy company. Ironically, it's a drink called an energy drink. That's the traditional nutrition facts. If you did a consumption facts and you did sort of conservative estimates of the embodied energy per container and the recycling rate and the landfill rate, and these numbers are sort of about right for this product. The scary thing is, if you were, personal energy footprint is based on a recommended 2,000 watt lifestyle, right? So if you were living to the recommended 2,000 watt lifestyle, drinking that drink once a day is 4.5%, right? And I think if you saw the world this way, you're like, screw that, I'm going to save it up and have another glass of wine tonight. Or, right, it totally changes. In some respects, this is part of a grand argument that we're phrasing the climate change energy problem incorrectly. And if we actually said, look, this is about quality of life for everyone, quality of, we're going to garden the whole planet, basically. We should just acknowledge that. And it's about the quality of life of all the people in that garden and how do you do things. then I think that helps you make more wise decisions about how we do this sort of stuff. And I think that's a much more constructive debate than the one we have right now. The debate we have right now involves a few angry politicians and a few defensive scientists, right? Because it's a very technical debate. If it was a debate about how are we going to, how do we increase everyone's quality of life, you'll get the musicians and the songwriters and the Bob Dylans and the artists involved. And not to criticize anyone in the audience, because I'm one of you, I think they're going to make more progress than we are on sort of the social change required. And rant. That's Barbie's energy. We actually made an online tool called What's On, and lots of people tore everything apart in incredible detail. Like, people would take their scales, and it's there's some obsessed people out there on the web. So I think these numbers are wrong in this slide. I've since corrected them, but I'll try and get them right now. And I think this is a point to, we've made the use of energy as invisible as we can this century. Like, you think about the process of buying gas. You take your big box and you go and park next to another magic box and you swipe your magic card, and 2 minutes later you drive away, right? What actually happened was they poured a mass of oil the size of you into that tank, and you'll do that again in 4 days. But you don't see it. It's like the most clinical transaction. The way you get your electrons for your light is a very clinical transaction. It's invisible. So this was sort of like experimenting with ways that you would visualize it. So imagine today when I left home at 7:05 to get the BART over here, what was the backpack I would have had to have as an average American? So it's not 67 pounds, it's about 10 gallons of oil, I think was when I redid the numbers on oil. The coal and the gas ones are grossly correct, right? But that's a pretty heavy backpack full of fossil fuels, and that's what we're all doing every day.
So these are additive numbers, they're not one or the other outcomes.
Additive, yeah. This is the 21 million barrels of oil that we use per day in the US divided by 300 million people. This is I can't remember the tons, this is the natural gas. Every one of us is doing this, right? And you can do fun things with this sort of type of thinking. You can say, we all drive cars sometimes, so we are all partly responsible as creating the demand for the oil spill in the Gulf. It's a shot glass of oil per day per person in the US, right? So you drove here today. I don't want to point fingers because, I poured a shot glass of oil into the Gulf today, right? And I think I would like to believe in a world where we start to take personal responsibility. And I actually think science is winning very, very slowly. We have some steps back, like the debate over Darwinism. But I think reason, I think it's a nice religion to belong to, this science one. And I think we're sort of winning eventually, and I think reason wins. But I think there's I think we're at the cusp now. If you think of the majority of articles in the newspaper, they're citing some scientific study and about the consequences of doing something, whether it be BPA in your child's drink bottles or whatever. And I actually think that maybe one of the ways you get some of the social change to have happen that you need to have happen is get people to understand really, we can build great models of things now, and to understand the personal consequence of every action, like like my shot glass of oil. That's, it's open for debate. That's a thought. See, now, once I go through the slides that are like prepared talk, and I get into the dangerous territory of having ideas in public. So, yeah, one of those dangerous ideas is we burn, that's the numbers. So it actually correlates perfectly. I know this is a tasteless slide, but I was trying to visualize how many barrels of oil we use in the US per day. It is the volume of the Twin Towers, almost exactly, right? And that's actually, I was always struggling to figure out why smog was as prevalent as it was. Like, I just couldn't do the math couldn't get the scale right for why there was smog over LA. But when you realize it's that much stuff you're burning and you can sort of get more of a sense of it. So this is entertaining. I think I was like, okay, so what if I want to generate all of my energy myself? It'll cost me about $40,000 to go and buy the solar cells with subsidies to nominally get the amount of energy I need. Big orange square is land area per person in the United States. The second orange one, that's land area per person globally. So 140 by 140 meters is average. I would need, for my 18,000 watt lifestyle, a 43 by 43 meter solar cell that's 15% efficient to give me all the 18,000. Globally, it's something like this. I have a slide somewhere that shows you that there are 13 countries in the world where you cover them with 100% efficient solar cells and they can't produce their own energy. Right? So if you do population density versus power per capita for those people. So the scary thing is I just bought a house in Bernal Heights and it's about 7 meters wide and 15, 20 meters long, right? So there's my house. If I cover all the land that I own, I cover about 1/3 of my budget and my wife and my kid get to starve and be cold. So this is sort of an argument, like there's so many people who really, the vision of distributed is really seductive, I really like it, but I think it doesn't quite add up, right? We still have to do lots of utility scale stuff. And again, open for debate, but all right, so I'll end there because we're into the dangerous section of slides. And yeah, okay, so questions? Great, critique.
My name is I'm a teacher, high school teacher. How would you summarize your lecture and what I as a teacher has to take back to my classroom in one sentence? I couldn't take notes.
Okay, so I'm going to answer your question really quickly and then I'm going to use your question to answer a question that I want to ask me. So I think I would say it's completely possible to have a good climate outcome for the generation of kids coming up, but we have to be really focused and we really have to do a lot of work, and it could be a really exciting time where we do a lot of fabulous things, but we've got to act quickly and do it. So it's not going to be a largely different message than what's available, but the message I would want your kids to hear is that reason helps. Logic and engineering and science can solve this with the willingness of the public. Like that's I want the kids to have that positive image. And then the question, the extension I want to go with is I think the problem with the talk I gave you, this is not terribly encouraging to go and give a 10-year-old, right? It looks depressive, it's really hard, it's going to be expensive. It's only going to be $60 trillion to do the whole project, so that's actually not that much. But it's not terribly positive. I think there's been a terrible failure, and I'm going to involve all environmentalists and all scientists to blame. We haven't done a good job of communicating the potential positive aspects. So I would want to say to your kids, how old are they, 11? 9 to 11, all right, 9. I would want to say, all right, how do you want to get to school in 20 years? Do you want to catch the bus, the diesel bus, or do you want to go by zip line or roller coaster? And I'm pretty sure they're going to say zip line or roller coaster. I'm going to say that's fantastic because light rail is 10x more efficient than your bus and the zip line is the most efficient of all, right? I think, and that is to say, I think we need to have a lot more positive visions of what the future could be for 9 to 11-year-olds. When I was growing up, we were still in the space race, and the future,